Okay, so let's begin today's conference. Today we are very happy to have Professor Daniel Spector from the National Taiwan Normal University. And today the title of his talk is The Problems of Dido. Let's welcome.
So, can you hear me? Very good. Let me put this here. Okay. So, thank you for the introduction and also for the invitation. It's a pleasure to be here. So, let me begin. And 我就要开始说，不好意思，我没有办法可以完全用中文介绍这个事情。一些是数学的问题，另外一个是我要说一些故事。然后讲故事的话，我应该要用英文，所以我开始这边就是 The Problems of Dido。我问你们一下，如果你要翻成 problem 到从英文到中文 ，problem 是怎么翻译？What is the word problem in Chinese? What's that? 问题。And what about Timu? Timu, what is Timu? What's that? What's that? Taitong. So, when you see this question, this is really the question. When you see this word problem, what do you see the meaning of this to be? There are several meanings. This is what I want to begin by pointing out, is that the word problem has several meanings. I want to ask you, when you see the word problem, tell me what one meaning is for you for the word problem. We're in mathematics, so the natural thing is what? What's that? Something to be solved. So we have mathematical problems, right? But then we also have other problems. And so when I use this word in English, the problems of Dido, I want to tell you about several problems that are not mathematical, and then one mathematical problem, okay? That's what I want to begin by saying. So this is a painting of Dido. Dido is the princess of Tyre. Does anybody know what Tyre is? Where Tyre is? So Tyre is what we call Lebanon now. Do you know where Lebanon is? Yeah, so Lebanon is in the Middle East. You hear about it recently because of Hezbollah and the battles with Israel, these things. So Tyre is a city. Lebanon is a country, but Tyre is a city-state in Lebanon. And this is at the time that Lebanon was underneath Phoenician rule. So the Phoenicians are an ancient people, and this ancient people would do a lot of trading. They would get in boats, and they would travel around, and they set up city-states. And one of their city-states is Tyre. And Dido, who is also called Elissa, is a princess. So the way that they had at that time, you know, also in ancient China, you have emperors. So in the West, you have princes, princesses, kings. And she had a brother, and her brother's name was Pygmalion. And he was the prince. And their dad is the king. And this information I tell you, by the way, here's a map of the Phoenician trade routes. So this is Tyre. This is Beirut. So this is Lebanon. And this is the island of Crete. And then here you have Africa, Italy, Africa, and then this is Spain. And this is where she was living. And she was living there, and their father was the king. And I think the first problem was she was married to a Cerberus. So this is her husband. And actually, it was also her uncle. So this, I think, is her first problem, is she was married to her uncle, and then the father dies. So he dies, and the kingdom passes to be led by Pygmalion or by Dido and Aceribus. And you can imagine in a place where people are competing for power, there was a problem. Also, apparently he had a lot of gold, and he hid it so that people didn't know where his gold was. And so Pygmalion wasn't happy about this because he wants to be in charge, and if his sister's in charge, then really his uncle's in charge, and he's not going to get power. So he killed her husband, he killed his own uncle, he killed him so that he could have power. Now, Dido didn't know about this. This was something he did in secret, and he did this in secret, and then it happened that she had a dream. And in her dream, Aceribus came to her and told her, he killed me. And then she said, I know what I have to do. I have to flee. So she fled and she left. And so there's Dido. There's the gold. There's other servants. And there's senators. So there's her and various people that are with her, and they took all the money. And then there's other people who, they have the king, but they also have other ways of doing, even in England now, you have kings, but you also have parliament, you have the House of Lords, House of Commons. So there's other people there that side with her, and they all flee, and they pretend to throw the gold in the sea, but they leave the gold, and they take the gold, and they throw some sand out there, and they all flee. And the first place that they flee was they fled here to Crete. And I was going to give a version of this talk to children, and I left out this part. They went to Crete, and they have all these people, but actually not a lot of women. So they went to Crete, and they picked up a number of prostitutes that were operating in Crete, and this became the part of this people that are together. So they pick up women in Crete, and they need a place to live. So you have people, you have a means to continue to living with gold, with senators that know how to rule, they have money. Let me ask you, what do they need? What do they need? They just need a place. So they travel and they landed here in Carthage. And when they got to Carthage, they needed land. And when they got there, they met a king, and the king was called Yarbus. And some stories say that he said, you can have as much land as you can tie off with the hide of an ox. And some stories say that she asked him for as much land as you can have with the hide of an ox. But all the stories say there was a request for as much land. So what is an ox? This is like a cow. So you take a cow, you take its skin, and you can have as much land as you can cover with the skin of a cow. So you've got gold, you've got servants, senators, and women. You've got to have a city. And what do you do with just the hide of a cow? So Dido was very clever, and she had the servants cut it up into thin strips. And I won't mark all the strips. So you make it up in thin strips, and then take it, and then tie the ends together. And then she said, here's the coast. So this is the coast. So this is where it is. There's a hill here, and we want the hill. We know hill is a strategic place. And then she said, now take the tied together ox hide and make a semicircle. And make a semicircle, and we'll enclose this land, and this is the land enclosed by the hide of an ox. Of course, this looks a similar size to this, but they got a very, very big piece of land, because if you take the ox hide and you cut it into thin strips, you get something very long like a wire, and they stretch it out. And this hill was called now, and the city is called, I think it's called Birth, or maybe I get the translation, but this is the word in that language for ox hide, and this is the city of Carthage that Dido founded in Africa. So she is the founder of the city of Carthage. Now, this is a very long story that I tell you for a math talk, The first thing I want to say is this is from 3,000 years ago. So I tell you this story from 3,000 years ago. How do we have information about 3,000 years ago? This is a book called the Aeneid by Virgil. The Aeneid is covering, so there's this thing called the Trojan War. And you may have heard about things like the Odyssey and the Iliad. This is another book in that spirit about the Trojan War, about a person whose name is Aeneas, which I have a picture of. Yeah, this is Aeneas here. So Aeneas is this person here. He was a participant in the Trojan War, and this Aeneas was written about in the Aeneid, and that's one source. But we also have the history of Trogus. So this is another person who is writing down history, and we have the Greek historian Timaeus, Menander of Ephesus, Flavius Josephus, and the biblical account of Solomon, king of Israel. So we have 5 or 6 different stories in history that we put together, and the story of cutting off a hill with the land of the height of an ox is in all these stories. And some of the stories differ in the details of what the dad's name is, what the brother's name is, what the husband's name is, but this is the story we get in all these accounts. And I want to tell you this because actually mathematics is a lot about history. So studying about what happened is very interesting. But now we enter into the mathematics. So you have a given amount of oxhide, and you want to cut off an amount of land. You want to get as much land as possible. So the question you're asked is, the problem, the mathematical problem, is given a fixed perimeter what shape is the maximum of area, right? So for example, you notice, and I can use this color here, you notice that this goes like this, but she also could have told them to do this, right? There's like a length here in which this length and this length are the same, but it's clear that this one has more area. And if you want to found a city, you want to get all your people to fit in there, you want the maximum of area. But what's not clear is that for a fixed parameter, meaning saying starting somewhere, this is difficult, but say for a problem like this, it's not clear that if you take a figure and you take some oxhide and you go like this, it's not clear that when you compare, and I don't know if these have the same perimeter, so I'm just drawing these things, I'm eyeballing. It's not clear that if you have these 3 shapes and use the same amount around the outside, it's not clear that this one encloses more volume, more area than the other ones, is it? Maybe you see something I don't see, but this is something that's not clear. So what we have in the problem of Dido is we have that intuitively, when you see some amount of area that you want to enclose or a fixed perimeter, that you should make a circle as the maximum, that you can't do better than that. But the proof that this could be done like this was not proved 3,000 years ago, and it wasn't proved 2,000 years ago. It was only proved in the last 200 or 300 years that this is this way. And this is the mathematical story that I want to tell you now. So we have, this is Dido and Aeneas. Before I get into that, just a few more pictures. Dido and Aeneas meeting, they met in Carthage. So after she fled, after she arrived in Carthage, this is when this Trojan war hero and this princess meet, and why we have her story. It's actually his story that she's a part of, that we hear about in the history. And this is a statue of Dido, which is formerly in the Louvre in Paris. And also, if you want the slides, I also include this information here so you know where we get the picture, who's it by, and where it's from, because this is a part of the culture of mathematics. We have to communicate not just what we're doing, but the references for these things. That's why this one's so small, is because I wanted the reference, and then I blew it up a little bit. This is the representation. This is engraved of where they took the oxide and they actually cut it up. This is a representation of this event. Okay, so now we go for the mathematics, and maybe I put the board up so that we can have this and this. Okay. So this problem is the so-called isoparametric problem. Isoparametric. So let's take a look at this. Let's say we have a ball of some radius, and we look at what the volume is. What is the volume of a ball of radius r? So let's say we're in n dimensions. N equals 1, 2, 3, blah, blah, blah. We're in some number of dimensions. What is the volume of a ball of radius r? Do you know this? Let me ask you in 2 dimensions. What is the volume of a disk? So this is r, and you look at the volume. What's volume in 2 dimensions? Pi r squared. And what about in 3 dimensions? You take a sphere of radius r. What is the volume? Four over 3 pi r cubed. So there's a little bit complicated number here. Maybe pi and 4/3 pi is not complicated, but a little bit complicated. And then there's a little bit simpler thing, which is this is 2, this is 3, this is 4. So what it is that there's the radius to the dimension is what it grows like. And then there's some number, which is some integral involving pi, which is a little complicated. So we usually write is actually it's the same as the volume of the unit ball. And the volume of the unit ball, we have a name for it. Sometimes we say the volume of the unit ball, we call it omega n sometimes, although that's not so important that we do that. That's what the volume grows like. Now, what is the measure of the boundary? We sometimes write per of the ball, which is to say the perimeter. Of course, perimeter in English is you have a house and you put your fence around the house, and the fence has some length which goes along the perimeter. What is the measure of the boundary? So this is the volume. What is the perimeter? What is the circumference in this case? 2 pi r. And what about in this case? That's very good. What about this case? Yeah, very good. Actually, this is very easy. Why? It's just the derivative of this, and in fact, you could think about that. You have the volume, you take the volume, and you move the volume of a little bit larger radius, and you take the derivative of that, and you have this small layer, and then you divide by the length, and you're getting exactly this number here. So actually, the perimeter of a ball is the radius to the power n minus 1, and if we just take the derivative of this formula, it's n times b1 times that. So this is the relationship. So what you notice about this is if you look at br to the power n minus 1 over n, so we take this and we plug that in there. This is b1 n minus 1 over n. Rn n minus 1 over n is b1 r to the n minus 1. I just write this and I just compute what it is at this power. And now I see that this number here is the interesting thing. So I say this is equal to, leave this alone, and I put this number here, n b1 r n minus 1. Now you can't just do that, right? You can't just put something in an equation unless you put it in two places, because this divided by this is 1, and so it doesn't change the equation. And so what we see is that the ball, which of course you have to change dimensions because the ball grows like r to the n and the perimeter grows like r to the n minus 1, so you need this factor. It's equal to this number right here, which is 1 over n b1 to the power 1 over n times r to the n minus 1, which is the perimeter of BR. So what we're saying is the volume, now I write it this way, the volume of a ball is equal to some number times the perimeter of a ball when you rescale the volume so that they're being compared in the same dimension. This is an equality. What the isoperimetric problem says is it says one of two things. You say fix the volume. So I say I have something of some volume. So fix the volume. The perimeter, so fix the volume. And you say that you have a set E which has the same measure as the measure of the ball. It says that the perimeter of the ball is smaller than the perimeter of the set E. So among all sets of a fixed volume, you do better by making it a ball. That's not what we have here. What we have here is somebody told Dido, or they figured out they have some fixed amount of perimeter. Or fix some perimeter. So you look at a set whose perimeter is E, and you say that you can use the same perimeter as the perimeter of a ball. And then what you have to have is that the measure, the volume of E, is less than the volume of the ball of the same perimeter. Let's take a look at this. Let's think about this a second. So what you're saying is you have a given amount of oxide. That given amount of oxide, you could use it to make a set E. You could use it to make a ball. Maybe E is a ball, maybe E is not a ball. But what you get is you get the most possible area when you make a ball. So those are two possible writings of this isoperimetric inequality. And when you write either one of these down in this form, you say this is equality. So that means if you fix the volume of a set E has the same volume as some ball. The volume of the ball can be written in terms of the perimeter of the same ball. And that perimeter is always smaller than the perimeter of E. You see what you derive is an inequality which looks like this. If you start here with the same perimeter, then you're starting on the right-hand side. The perimeter of a set E is the same as the perimeter of a ball. The perimeter of a ball is equal to some constant times the volume. The volume is bigger than the volume of E, and you find that you get the same inequality. Is that the isoperimetric problem, when you formulate it, turns out to be a functional inequality. Turns out to be a functional inequality. Now that's what we do in the modern times. Let me just go through a little bit about the arguments here because I think it's a little bit easier. So we like to do a little bit easy and then a little bit hard, and then we bring you back to something easy again so you can stay with me. I know there's other things to think about, but so in 150 BC, Zenodorus is a Greek mathematician, And I think we have him to thank for things like limits, like when you say that you shoot an arrow, and I think he had the argument that an arrow can never arrive somewhere, because in order to arrive there, it has to go halfway there, and then it has to go half of the remaining way and half the remaining way, so an arrow never arrives somewhere. But of course, we know an arrow arrives somewhere. So this is early ideas about calculus, and he had a lot of interesting ideas. 1, if there exists an n-gon, what is n-gon? What is n-gon in Chinese? I heard this word. What's that? 针多边形. Okay, an n-gon having the largest area among all n-gons of a given perimeter it must be regular. Let's draw what that means. So we're going to allow you a given amount of perimeter. And we're going to go given amount of perimeter, and we're going to look among all objects with 4 sides, and we're going to draw a bunch of objects. If there is a maximum, it's the regular one. And he proved this. 2, among regular n-gons of equal perimeter, more sides equals more area. So you compare the square, the regular pentagon, triangle. Of course, this is very bad because I can't make sure that I'm drawing the same perimeter every time. But the regular one, this has less area than this has less. So the area is increasing with the number of sides. And 3, the circle, of course this is not good, I should draw it a little bit closer. The circle of the same perimeter has the largest volume. Now let me ask you a question. If you are able to prove this, this, and this, does that prove in the plane that the circle is the best? So this problem of fix perimeter and maximize volume does this tell you that the circle is the winner? So there's a clue right here. If there exists an n-gon, and this is a clue that there's something missing here, and it's something that actually the way people looked at mathematics back then in the Greek time, so before we were in 3,000 years ago, and now we're 2,000 years ago, and soon we'll get to the present day. But 2,000 years ago, they were writing these things down, and they didn't have the way of thinking about things that we do now, which is that there's a question of existence. And this is a question that's not developed. It says, okay, we're not sure that there is a maximizer here. We're not sure there's a maximizer, which means that when you select among all 4 four-sided figures that the square is the best, you didn't know that there was a best then. Of course, this line of argument is rigorous, is that it's not difficult to show, because if you look at 3-sided figures, 4-sided figures that are regular, there's exactly one of them, and you can compute the area. This is an interesting problem, by the way. I was in high school, And I thought about this. And you can take it and you can divide always up into triangles because that's what it means to be a regular figure. You can divide it in triangles. You can call this angle theta, theta n. And then you can use this formula for the area of the triangle. You add them up and you can find that the area of these things is something like a sine function that you have to look at. This is an interesting homework exercise for you, by the way. So you can really show that this works, and you can really see that this area is bigger than this, but you don't quite have a way to say that among all four-sided figures that the regular one is the largest. And this was a problem in 150 BC, and this remained a problem. This remained a problem up until the 1800s. This problem is a problem about compactness. Now let me ask you, if I say the word compactness, do you have any, what are your feeling about compactness? Do you know what that means? Who has taken Gaodong Wei Jifen? No? I think maybe you've taken that. Yes, I know. So you've all taken this. So when I say the word compactness, maybe it's a difficult word in English, but let me ask you something. Let's say you have a sequence, xn, and the sequence stays on a bounded set in our xk. What can you tell me about a sequence? So you have a ball, and the sequence is just staying in the ball. What do you know about that sequence? What's that? Yeah, Rn. Very good. In Rn. You have a convergent subsequence. Up to a subsequence, xk sub l will converge to, so there's some point x which is a limit point of a subsequence. That's what compactness is. This idea of compactness is exactly what's going on here, and what's missing here is you have lots of possible choices of figures, and the sense in which you have some kind of compactness is missing. And so that idea needs to be made precise. So the idea that came in the 1800s, this brings us to the calculus of variations. So we talk about functional inequality calculus of variations, which is pioneered by Euler and Lagrange. Also, we remember that Bernoulli and Newton had used these in these problems, these brachistochrone problems. This idea is developed in the calculus of variations, and there's an idea here, which is, let's say I have some figure, okay? Let's say I have some figure, and I think this figure is a good figure, but I want to find a figure which maybe is better. And what I'm going to do is I'm going to fix the volume, and I'm going to decrease the perimeter. So remember, we can always do one or the other. We can always fix the perimeter and make the volume bigger, or we can fix the volume, make the perimeter smaller. This is the same way that we're talking about to solve the problem. If you draw a line here, and you move the line from left to right, at some place you find half the area, right? You move it across, at some place you find half the area because the integral is continuous with respect to translation. So there's some place you find where it's exactly half the area, and then the right half and the left half don't look the same, but if you go and you look at whichever one is a little better, you can put a mirror there, and I'm going to have trouble. This should be symmetric. If you find the place where you have half the volume, you can take the left and the right half, the perimeters, and whichever one is better, you can put it on both sides, right? So they don't have to be, one of them doesn't have to be better, but at least they're the same, or maybe one's better. You can take the one that's better, and what this does is it keeps the volume between this and this the same. And if you choose the half that the perimeter is smaller, then you have the perimeter on one half and then the same thing on the other half, because you're saying that this right here has a smaller measure of perimeter than this. And maybe I chose the wrong half here, but you're saying this is smaller. And what you've done is you created a shape which is now a little bit more symmetric, and the perimeter is smaller. So you do this once, And then you can go and you can do it again, and you can do it in this direction. And then you can do it in another direction. You keep seeing, you keep doing it in different directions. What you're ending up with is you're ending up with something which is rounder. This is called Steiner symmetrization, by the way. And this argument, you find a sequence in which you're doing this. This argument is not quite enough to lead you to, in the limits you find something where you have something which is totally symmetric and which is really the maximum. And what's missing is exactly this compactness. You have a sequence of points in Rn, and you can find finally a limit point that you end up at up to a subsequence. When you do this, you have this sequence of sets in Rn, and to find a limiting set that you can guarantee that you converge to is difficult. And the reason is that this is happening, even if it's complicated in several dimensions, it's happening in finite dimensions. Your question, you say finite dimensions. The space of all sets is not a finite dimensional space. You can take a set and you can perturb it a little bit this way or a little bit this way, and you can actually find an infinite number of different directions, and that's one of the points of the calculus of variations. So now I have about 12 minutes, I think, left in the talk, and I want to say a little bit more with this inequality. Now, this inequality is really deep, and it's really beautiful, and it's very important that you get exactly this number. Because if you don't get this number, then you don't really prove exactly this very deep thing in the calculus of variations, that the ball is the one where you have equality. But if you want to get constants that are exactly right, you have to work very hard, and you have to do a lot of mathematics. Maybe it take me 10 pages to show you that this works with exactly this number. I want to show you something which is much shorter, and you get a constant which is bad, but it's very beautiful because it connects a lot of areas. So you have this problem. The problem is the heat equation. You take here's Rn, and here's T. You take some initial heat distribution in the room, and then you wait a little bit and you see what happens to the heat. And so here's a slice here, and a little bit later, the heat happens here. So for example, in one dimension, you take heat and you put a little bit of heat in one little place, and then you wait a little bit, and after just a little bit of time, just a little second of time, the heat does diffusion, and what happens is, of course, this is very sharp drop-off, but there's still some, but you have heat in some spot, and then you wait a little bit, and you get heat everywhere. This is the heat equation. The heat equation has a solution which is given by the convolution of two functions, the heat kernel with your initial data, Now, the reason we want to use this heat equation is because we know something about this heat kernel. We know this heat kernel, that if you measure its integral in L1, you start with it's 1, okay? And what is this saying? This has to do with the preservation of the amount of heat that you start with and the amount of heat that you go to. We want to use the fact that if we take the derivative of this heat kernel, if you take a derivative of a function like this, what you end up getting is the derivative of an exponential. So the derivative of e to the minus x minus y squared over 2t, you can compute this. It's the derivative of the exponential, 4t. And then you need to take the derivative of this function. So we need to take its negative 2x minus y over 4t. So times this vector quantity. So when we measure the derivative of this function and we do this integral, what we find out is that here you have a t and you have x minus y squared. What that tells you is t to the half behaves in scales like x minus y. So what you get here is you get a t to the half and a t to the half, so that the derivative of the heat kernel has a certain behavior by scaling. So you can, by the way that you can see this, if you integrate e to the minus x squared over 4t and 1 over 4 pi t to the dimension over 2 and dx, how do you resolve this integral? You know this one. How do you resolve the Gaussian integral? Use polar coordinates, right? So you can do it in one variable by polar coordinates by doubling the number of variables. And so you use polar coordinates to this, and this number here and this number here, that's exactly the balance for which this is 1. Actually, if you rescale it, you understand that by rescaling, it's some constant, which you don't know that it's 1, but it's a constant. For this one right here, you can do the same thing. You do a rescaling to see that it's a constant, and then it's divided by t to the half. Okay, this is what we need to continue. So with this information, we can look at this right here. Now what is the derivative of a set? You take a set in Rn, and a set in Rn, if the set is smooth, there's a normal to the set, and the derivative of a set is the normal to the set, and then there's a measure that lives on the boundary. So there's a normal to the set, and then there's some measure, which maybe you've seen is the Hausdorff measure on the boundary of a set. Actually, for a large class of sets, you can talk about what the derivative is. There are certain objects for which this makes sense. And I believe a lot of you had you taught them distributions, right? Not these 2 or 3 years. So what it is you can talk about the derivative of a set. You can take the derivative of a vector function, and you can integrate it over a set. And sometimes you can integrate by parts. And this is what we call the distributional derivative of this set. So this is what this object is. Now, you use Holder's inequality. Holder's inequality, you can go up by the L infinity. And you get this one in L1 and this one L infinity. You can use the convolution inequality. When you have the heat kernel in L1 and the derivative in L1, what's the L1 convolution inequality? You can get it by this one in L1 and this one in L1, or this one as a measure. So this is, if it's convolution with a measure, this is less than this. For this one, you can take the derivative and you can move it over here, so the derivative is here. L infinity can go by this one in L1 and the characteristic function of the set in L infinity. Now this is bounded. This is 1. This is what it is, and this is t to the half. And so what we've just shown, and by the way, I just found this in a paper recently, is a very nice inequality that I saw there, is that what you can find is the derivative of a set controls this quantity. And now if you add to this the Fourier transform, what does the Fourier transform turn convolution into? So by the way, if there's things you don't understand, I make the list here. Really interesting things to study are the distribution theory, the Fourier transform, and maybe PDE, but especially the heat equation, because if you study the heat equation, you have a powerful tool for all of analysis. These are things for you to study in case there's some things you want to look at here. The Fourier transform turns convolution, it turns it into multiplication. So this is the Fourier transform of this object, and the derivative gets turned into, so derivatives in real space, Fourier transform into polynomials. So by the way, if you're not interested in analysis so much, you're interested in algebra, the fact that the Fourier transform turns derivatives into polynomials means that algebra can be very useful in analysis, times the Fourier transform of this object. And we also know that the Fourier transform is an isometry on L2, which means that we can take this whole thing and we can square this here. So this inequality tells us that t to the half times this integral of e to the minus 4 squared is 8 pi t psi squared times mod psi squared times 2 pi squared chi e hat squared d psi is less than the derivative of that. Now, in order to save a little bit of time, because I think I'm almost done, in order to save a little bit of time, when you have this Gaussian, what you see here is that when c is really big, that's not a big contributor of this integral. So what you can do is let's call t to be 1 over r squared, so that the t comes here, so that it's c squared over r squared, it's c over r. This means you're in a ball of radius r. So this tells you in a ball of radius r, you can get a lower bound with 2 pi squared e to the minus 8 pi squared divided by r psi squared chi e hat squared and d psi is lower bound. So that means that's still smaller than the derivative. Now I claim the following. So to save time, I claim the following. If you take this and you multiply both sides by 1 over r squared and integrate from little r to infinity in dr, if you multiply by 1 over r squared and you integrate, you'll get a 1 over r on the right-hand side. If you multiply by 1 over r squared and you have this r cubed, you have something a little bit complicated here. But what you have to do is you have to use Fubini's theorem to change the integrals. And it would take me probably 5 more minutes to do this, but in order to spare the time of the 5 minutes, when you do it, there's one term that pops out like the term that you have, and there's another term that pops out, which is you end up with psi e hat squared on the outside of the ball. So you integrate from r to infinity, you end up with one term which is outside of a ball. And what you find is, by moving things around, is that this is less than or equal to 1 over r d chi e. So you have this inequality that came from here, you have the Fourier transform, and then you integrate and use Fubini's theorem and you get this inequality. And now we're ready for the conclusion. The measure of chi e in L2, well, it's a characteristic function. whether it's squared or it's not squared, it doesn't matter. This is just the measure of the set. The Parsifal-Plancherel identity tells us that this is the same as the Fourier transform in L2. This is equality when you're on Rn. This is the integral in a ball of this characteristic function, Fourier transform, and the integral outside of a ball. But you know that the Fourier transform is less than the measure, because the Fourier transform maps L1 into L infinity. So this is less than the measure of this ball, which is a constant. So we're going to put this thing here. We're going to forget about constants. R to the n times the unit ball times the measure of E. But this is the measure of E. So if this is squared, this is the measure of E squared. So you get a measure of E squared here. This is nonlinear. This term is what I just told you about here, plus 1 over R times the perimeter. So it's really interesting. The measure of E for any R can be controlled by the measure of E squared times R to the n plus 1 over R times this number right here. So you have an inequality like this. When R goes to 0, this thing goes to 0, and this thing goes to infinity. When R goes to infinity, this thing goes to infinity, this thing goes to 0. At some place value of R, they're going to be equal to each other. Or you can do calculus and you can find the optimum in R of the right-hand side, but we've already thrown away constants, so we don't care so much. So a good strategy, by the way, is to set this equal to this. And when you set these two equal, you're saying, let me let R to the n, measure of E squared, equal to 1 over R d chi E. So you move the R's over, so R is equal to d chi E divided by E squared. Of course, we know the measure is not 0. We're not taking things that have 0 measure. We can divide by that to the 1 over n plus 1. So this is the value of R, which is more or less the optimum here. And then you plug that in. You plug that in. And when you plug it in, you'll start on the left-hand side, you'll have the measure of E. You've thrown away lots of bad constants in the process of doing this, but you'll get R to the n times E squared. So what we'll get is we'll get E squared times R is this number here, d chi E over E squared to the power n over n plus 1. So now you have to do a little bit of arithmetic here. This is 2, so this is E to the 2 times 1 minus n over n plus 1. This is n plus 1 minus n over n plus 1 is E to the 2 over n plus 1. So we're going to take that and we're going to move it over, and we're going to get E to the 1 minus 2 over n plus 1 is less than d chi E Rn to the power n over n plus 1. But what is this number here? This is n plus 1 minus 2 is E to the n plus 1 minus 2 is n minus 1 over n plus 1 is less than d chi E to the n over n plus 1. So look, there's n plus 1 here and an n plus 1 here, so they cancel. So what this is this is E to the n minus 1 over n is less than d chi E of Rn. And this perimeter is exactly what this object is. And so what you see here is how the heat equation, Fourier transform functional analysis, can give you insight into this inequality, which in the sharp form is the isoperimetric inequality. And that's all I want to say today, so thank you for your attention. What's that? It was here. It was right here. So something that this, by the way, this is a very interesting. what it is something that people you talk about a lot of times. Is you have these estimates. F convolved with G in L1 is controlled with F in L1 and G in L1, right? This is just Tonelli's theorem or Fubini's theorem. You do this. F convolved with G in L infinity can be controlled by F in L1, G in L infinity, or the other way around, whichever one you want. So these two inequalities. These two inequalities are called by Stein to be the fundamental inequalities. In fact, if your convolution is not commutative, then you should record 3 inequalities. And this is used by Stein to define an operator that if TFG satisfies these 3 estimates, you call T a convolution operator. So structurally, you say something is convolution if it's bilinear and satisfies these 3 estimates. And once something is a convolution inequality with this structure, you can prove lots of things. So this is called convolution. What I noticed is that sometimes you have convolution with BV functions. And with BV functions, these estimates, they're linear estimates. What I noticed is with BV functions, with functions of bounded variation, is that a lot of times instead of working with this, you can work with the derivative of a characteristic function. And when you work with the derivative of a characteristic function, in addition to the usual convolution estimates, you have 2 more estimates. And those 2 estimates are you take the derivative and you put it here. And when the derivative is here, what you can get is this is less than the derivative of that, so that's 1 over t to the half times the measure of e, and that's less than, in L infinity, you move it over here, that's less than 1 over t to the half, independent of e. So that for derivatives of characteristic functions, you have these 2 nonlinear estimates, and these 2 nonlinear estimates can give you Sobolev inequalities. But not only for here, you have lots of examples of where you have these nonlinear estimates arising. And it happened, I looked at a paper and I said, oh, these nonlinear estimates could be useful here. And they are useful here. Thanks for your question. So I throw away a lot, but actually I was thinking about this as I was driving here because, you know, you have nothing else to think about on the drive. And I realized that you throw away all this, but you don't have to throw away, because what you could do is you could write the integral of pt convolved with chi e. We could write this, and we could use the fundamental theorem of calculus. So let's take the derivative d by dt of this and integrate from 0 to r, right? So you take d by dt and you integrate dt. So what happens when you use the fundamental theorem of calculus? This is on the one hand equal to pr convolved with chi e, right? You evaluate the endpoints, minus p0. What is p0? That's the identity, because pt at 0 is the identity, minus what we get is the integral of chi e squared, which is just the measure of e. So this is equal to this. But on the other hand, you can take the derivative of the heat kernel, and then you take the derivative of the heat kernel, and then what you'll get is you'll get the Laplacian. So you get pt. So the derivative of pt is the Laplacian of pt, and then you can integrate by parts. And if you integrate by parts, then what you'll get is you'll get this is equal to the integral from 0 to r of pt convolved with the derivative chi e with a minus sign times the derivative of chi e. And the heat kernel is a semigroup, so you can write this as pt over 2, so that this pr convolved with chi e, and you can also use the semigroup property there, minus the measure of e is equal to the integral from 0 to r of the integral of pt over 2 convolved with d chi e squared dx and then dt. And now you have this thing with r. So now this is an equality, and you have an equality which relates the measure and the derivative, and this value, the heat kernel. So this is a possibility of doing something closer. And there's a precedence for this if you look at optimal transport theory. In the optimal transport theory for the Sobolev inequality, you start with the function g, and you look for solutions of divergence of a function is equal to that g, and then by optimizing in g, you can find actually the sharp constant in the Sobolev inequality. I think that either varying PR or with a good choice of R, there's a possibility of a sharp constant here. That's what I'm thinking about.